Hi everyone, this is Hossein Kashiani from West Virginia University. In this presentation, I'm going to explain my paper, which is Robust Ensemble Morph Detection with Domain Generalization. Face morphing is an image manipulation technique in which two look-alike faces are blended together to form a morph image of high quality. A successful morph image should both fool humans and face recognition systems. At the time of passport enrollment, the passport photo can be easily manipulated with a morphing attack. This ultimately poses a security threat in border control. As a result, a high-performance morph attack detection is vital to retain the security of border control. Although there exist several studies in morph detection, all of them assumes that the source and target morph data are independent and identically distributed. This assumption actually neglects the domain shift challenge in real world for many morph images. As a result, a learning agent that is only trained on source data when applied to out-of-distribution samples perform much worse. In addition, despite the success of deep CNNs in morph detection, CNNs are also known to be susceptible to another type of attack, also known as adversarial attack. An adversarial attack attempts to generate an adversarial example with perturbation, which actually force our model to output wrong prediction. In this regard, the vulnerability of morph detection systems to adversarial example have serious consequences. In this paper, we propose a morph detection model that highly generalized to a wide range of morphing attack. We achieve this goal by incorporating the capabilities of both CNNs and transformer architectures simultaneously. We also improve the robust accuracy of the Ensemble model by using multi-perturbation adversarial training and generate adversarial example with high transferability for several single models. At the end of the story, we carry out several experimental evaluations to validate that our robust ensemble model gained better robustness against several adversarial attacks while can outperform the other state-of-the-art studies. A single model converged to a local minimum. However, an ensemble of single models with different, for instance, initialization weight or loss function can provide a better and faster convergence to a global minimum. This is because different single models usually do not make the same mistakes. Inspired by this fact and by ensemble learning, we construct our model from several state-of-the-art individual CNN and transformer models. We experiment different models and ultimately select 2 transformer models and 1 CNN models to construct our proposed ensemble model. The CNN model that we use in our ensemble model use residual morphing noise for morph detection. The residual morphing noise usually exists in high frequency patterns of a morph image. These actually can model the morph manipulation, and this morph artifact can be useful for the ultimate goal, which is morph detection. As a result, we try to learn a CNN denoiser to calculate the residual artifact of the morph, and then we try to train an inception ResNet for morph attack detection. This is our ensemble architecture, which is constructed from 2 transformer models and a CNN model. The transformer models are Whitby 16 and with L32, and the CNN model is the inception model that uses residual morphing noise for morph detection. To improve the adversarial robustness of our ensemble model, we adopt adversarial training with model-based ensembling attack. In this approach, we aim to fool several white box models at the same time to create highly transferable adversarial example for adversarial training. The white box model in our paper are the one that create our ensemble model. To evaluate the generalization performance of our model, we ultimately test our model on several unseen morph images dataset. The dataset that we use include, for instance, Ferret, FRL, FRGC, and AMSL. Also, we use different morph attacks such as Face Morpher, OpenCV, WebMorph, MIPCAN, and Print and Scan attack. We also perform two ablation studies to find the best configuration of our ensemble model. In the first one, the number of single model and their combination are studied, and in the second one, the fusion method is studied to construct the ultimate ensemble model. These are the results of our first ablation study. These studies reveal that the ensemble model with B16, with L32, and noise aware ResNet, and the feature-based superlearner components outperform all other variations for constructing our final ensemble model. So we fix these components in our ensemble model. The performance of our ensemble model in white box and black box settings in these studies also indicate that the proposed robust ensemble model gains substantial improvements over the baseline ensemble model. We also make a comparison between our method and various state-of-the-art studies. This experiment also carry out to find out whether the multi-perturbation adversarial training can hurt the clean accuracy of our ensemble model or not. And as you can see, the result demonstrated that the proposed robust ensemble model can maintain its superior performance on clean accuracy and also can significantly outperform the other state-of-the-art studies. And these prove our paper at the end of the day. These are the references that we use in our presentation in the previous slides. And finally, thank you for your attention. If you have any question, I would be happy to answer them.